Okay, it's not the best title. I had to come up with something quickly. So really glad I'm here. I'm really grateful for the invitation. It's my 5th visit to New Zealand, and I love coming here. It's just the flights that don't do it for me. But WGS, whole genome sequencing, it's also used as whole genome shotgun sequencing, and food safety. Is it the best thing since sliced bread? Probably. But why sliced bread? Well, one of the things that I always talk about is disruptive inventions. These are the things, the game changers, that something comes in and suddenly changes the whole platform or anything that's doing. Sliced bread was one of them. Suddenly it became easy. But a very early example is the 4T, when suddenly the assembly line came into production, and it wasn't like somebody making something. Something was suddenly quickly made and sold. If we go more modern, we have things like the compact disc, the iPhone, Napster, Spotify, all these kind of inventions that suddenly changed the way we're working with things. And you can basically see it as that there's the low, medium, high quality use and the most demanding use, and that new technology suddenly changes everything and goes way beyond what we're doing with the old stuff. And genome sequencing has been one of those technologies. And one of the things that we all know about is during the COVID period, that we basically were managing to follow what kind of types of COVID there were, how they were quickly spreading across the world, because people were sequencing their COVID strains from wherever they came, and they were sharing the data. Now that is a more complicated issue. They're sharing the data so that everybody could follow what was happening. And so that's why we knew was suddenly certain types like Omicron and so on were where they were and how quickly they were taking over in those waves. But what is whole genome sequencing? This is a picture I'd drawn ages ago. And it's still a simple way of saying it. Basically, we have a piece of DNA or RNA that we converted into copy DNA, and we fragment it. We just use some mechanical shearing or enzymes. We put some adapters on the end so we can basically manipulate them. We immobilize them on a slide or a picoteter plate, something like that. And then we basically, rather than doing directed sequencing, what we used to do before, we basically sequence everything that's there. Don't bother about doing anything targeted, just do everything. And then let computer programs make something of it. So the whole difference was not targeting, but basically going ahead, doing everything, and just let software decide afterwards. And so we now have really 3 main technologies after a lot of wars between the sequencing systems. It was already mentioned Illumina, that's the market leader. It's a very high data yield, very short read, so you have a lot of computer work to do to put it together. The machine is very expensive, but the sample cost is low, because you can multiplex a lot. Now the 2 competitors are PacBio, which is not as high producing, it's expensive machine, and the cost per sample is very high. So it's not one that you just easily do for every sample you have. And then there's the nanopore that was mentioned in one of the previous presentations. That's also, it's a low output, medium output one. You get very long reads, so you don't have to do a lot of computing on it, comparatively. And it's cheap, and it's a very portable piece of equipment. But the cost of the sample running is still very high. So remember, this is about, you can only pick 2 out of the 3 things that you want. You can have it cheap and good, but then it won't be fast, etc., etc. The portability is an issue, is really something that's coming to the fore. So the nanopore is great because it's the size, the MinION is the size of a USB stick, for those who still work with USB sticks, because I've been told that the younger generation already don't know what a USB stick is anymore. And that makes me really feel old. But you can see it here, this is a MinION, and somebody's pipetting in that. You can take it anywhere, so it's very portable. Now, what are the good things about sequencing? Well, it's great. Otherwise, we wouldn't use it. This is an example from the outbreak of listeriosis in South Africa, where they basically had an outbreak with processed meats, and they could target it down to a factory where it all happened. And they did that with whole genome comparisons. And basically, if the numbers that you see where the samples are linked, there's the number of differences that they found. If it's 4 or less, they are the same isolate, taking into a little bit account of technical issues. If it's more than 4, it's different. You can see that line above which says 14. That's the separation from the islets that are non-related to the outbreak. All the human samples, the orange ones in there, were all samples from the same outbreak. So they could really target it to that factory. So when it works, it's absolutely great. And we have data sharing, public repositories. I know the industry will flinch when I say data sharing, I know that, because there are some issues that I'll come back to. But when publishing something about where you've done sequencing, you have to upload it into a repository. They are mostly at the NCBI, but there are also other initiatives like PubMLSD and Entrobase. And that means that, for instance, on E. coli, we got probably 500,000 E. coli sequences that we can look at. Salmonella, we're getting close to the 1 million, although they're not all unique. There are some shared in the databases, but there is so much information out there. Campylobacter, my favorite organism, loads of data. Too much. Actually, my computer crashes when I try to do too much on it. Listeria is still there, but it's good. So lots of data because we share, but then there are also coming some disadvantages. Because once you have the pros, you get the cons. Is WGS perfect? Well, perfection doesn't exist. It's a road to somewhere. It's not a destination. So you try to get it perfect, but you never will. I like the Salvador Dali quote. I didn't look up where it's a real quote from him, because remember, this is this misinformation that we talked about. I said, have no fear of perfection, you'll never reach it. Maybe you can tell me whether it's real. So what are some of the problems? Well, one of them is underrepresentation of certain continents or areas or types. And I've given here 2 examples of my own stuff. I looked at Listeria monocytogenes, of all the genomes that were in the database. You can see yellow, that's American. There's a bit of Canadian in there, but it's primarily American. More than half of the samples are American. Most of the rest is European. There's these little ones which are from Asia. Well, Asia is a big continent, and it has a very small contribution to the number of samples. I call it Oceania, don't attack me on it. I just meant for that, you know, Australia, New Zealand, and everything together. And there is a blue one, which is Latin America, which is pretty small compared to the number of people are there. And there is actually a black line, which is Africa, but you can't see it on the slide there. There's virtually no African islets. So there's types of Listeria which are not represented at all in the databases. We don't know about them. The other thing is in Campylobacter, the US actually doing it quite nicely because, you know, the yellow is farm animals, red is poultry, blue is human. There's a nice distribution of them over the years. In the UK, we're doing it completely wrong because we're pretty much only sequencing the clinical isolates. So how do you know what makes a clinical isolate the one that caused infection if you can't do the comparison with what's out there in the environment? So you need more surveillance, not just doing sequencing clinical isolates. So, ideally, we would have surveillance and random sampling. Problem with that, it's very high cost. It's really expensive to do. It's very labor intensive. The Americans do it by having loads of labs that they gave a lot of money and free sequences. But that's not a sustainable model for every country. It can also be very intrusive because, you know, they go to farms, they go to supermarkets. Do you think those farms and supermarkets are always really happy with, you know, these people coming in and taking samples everywhere? Probably not. Same goes for patient samples and everything. So this can be really problematic to get the samples. You require then transport, bacterial growth, which means that you may select for specific types, the ones that survive the process. So you don't have an unbiased analysis. Now, data sharing, I mentioned that, and commercial sensitivities can clash really badly. Not everybody wants to share their data because there will be repercussions if those data become public. So you really need to be careful that what you have in the public domain may only be the stuff that didn't cause that problem. Data analysis, I know a lot about that. It's often not costed. You know, people come to me and say, oh, we forgot to cost it in the grant. You press a couple of buttons and there will be an outcome, is there? So it's not costed, it is complicated, and it does cost time. Statisticians will know what I mean with that. They're also often not costed in the proposals. And it's pretty much only available to high-income countries, not to low-income and middle-income countries. So that's what the data availability thing came. Maybe we can use the Oxford Nanopore once it becomes more available and more affordable, where we can actually skip that whole process of transporting samples and growing them, and actually go a bit like Leon in one of his questions suggested. We may go metagenomics and actually sequence whatever's in there in the sample straight away. Will be difficult. But there may be a better information. And then finally, not everything requires the best technology you have. Sometimes you can just do with a simpler test. So we could actually look for things like antimicrobial resistance genes, ESBL genes or something like that, but basically simple LAMP amplifications. LAMP is a linear amplification, so unlike PCR where you have cycling of different temperatures, you can do a LAMP just in a water bath. So you don't need any technical provisions, you can just bring it on site. And so that is one of the options, and here's one from a project we've done for the European Union, is where our partners in Ireland made a lab in a suitcase where you just go to the farm, you take your fecal samples and you process them, all in one suitcase. It's very good exercise as well because it's not light. And we made one for water samples, so we can actually test what is there that comes out of the water pipes. And you also need independent analysis and unbiased analysis. So we have a smartphone app that we are developing where basically somebody just does the experiment, photographs the outcome, it gets sent to a server, and that then analyzes what the outcome is, rather than the person there saying, ooh, I think that may be positive, or I want that one to be positive. So there is lots of things that we can do to improve it still. So as a conclusion, the genome sequencing, the WGS, it's really great. It's highly informative. It will tell food industry and regulators a lot. But we need to now think about how can we actually make risk assessments from these data, because that's the one thing we can't. If you give me a genome sequence, I cannot tell you if that one is going to be the one that does the next outbreak, because we still don't know really what makes a pathogen a good pathogen. So how can we get those data converted into something that actually tells you about the risks? And a question like that is any listeria a problem, or are there specific troublemakers? Well, it's probably any listeria is bad, but do we know that for sure? Can we use the power of data sharing while being sensible about the need for confidentiality? Now, that's going to be a struggle, but it's something that needs to be discussed. And then important to get a setup of a surveillance just to make sure that we're actually not just testing the samples of outbreaks. We need to have a comparator. So we need to think more about where we get the samples from and what we sequence. And with that, I'll stop now and hand back to Lucy. Thank you for your attention. Did I stick to time? I think so.
I did send an email warning them that that Glenn would have to physically remove them.
That little hook that comes out on the stage.
Any questions at all? Patrick?
I can probably shout.
Yeah.
Thanks, Arnoud. So, with the listeria sample, with the ST6 listeria, you mentioned that 4 SNPs made them clonal.
Mm-hmm.
We've had this discussion before, but I think now with Nanopore and the availability of getting those whole genomes as circular much easier, do you think that idea of when a clone is not a clone needs to be changed?
Yes and no. I mean, you got to remember, this was not a SNP. This was a core genome amylase comparison. So it was 4 alleles different. So that's probably, it's more than 4 SNPs, I would say. So this is just a technical discussion, apologies. But basically, yes, technology will change and will get better. So we'll probably, at some point, we'll have to discuss this threshold. The problem lies in that this threshold of 4 will work for Listeria, but will be completely useless for a Campylobacter or an E. coli, because there's a lot more variability in those bacteria. So that threshold will need to be set for every pathogen separately. And Get a few scientists together in a room, they will disagree about anything. So that's going to be a struggle.
So we know further forward.
Yeah.
Thank you.
Any other questions? Arnoud, you had a laboratory in a box on your
Sorry?
slide there. You had a laboratory in a box.
Well, I don't have it, our Irish partners made
Okay,
that.
your Irish partners. How long do you think it's going to be until we see something like this being used by people to test their own food, their microbiome, and some of the implications for that?
I'll be honest, I think personalized medicine, so that people actually do a test for whatever genetic disease and so on, will come earlier than I think that people testing their food. Because if you imagine, you know, we eat so much food, we eat so many meals, that it would become way too expensive to test that much. It's a bit like a COVID, you know, the UK government handed out a lot of COVID tests, cost them a lot of money, well, cost us a lot of money as taxpayers, and still there weren't enough tests to do. And that was only one test every couple of days for most people. So I don't think it's currently affordable to do that. But we should work on it. The problem, of course, is that it's not just, and this is why we had this Android app, it's not just about testing it, but also being able to read out. How well do you think the COVID test will read out by people? Because people have a reason not to want to be COVID positive. So they look at that line, and if it's really faint, I think I'm negative today. So there is this issue, and do you really want to eat the food or not? So do people actually want to test their food? So I think it will still become more of a regulatory tool rather than a personal tool. But it's the same for genetic diseases. Do you want to be tested for certain genetic diseases?
Any other questions?
I may want to, but I don't want anybody else to have that information.
Any other questions for Arnoud? Okay.
I'm available afterwards.
Yeah, I can find you for coffee. Thank you so much, Arnoud.